One of the viewers has an Instax SQ40 instant camera, but he misplaced the battery cover. He scanned the battery compartment in 3D and sent me the file asking if I could walk him through reverse engineering the cover. This is the 3D scan of the viewer's battery compartment. It shows 3 openings, one for the push-in plastic lock and 2 tabs at the bottom. Looking at the recess along the edge, the shell seems very thin, maybe under 0.5 mm. There are 2 lashing areas for the cover marked by the arrows. They let the push-in lock flex and release when pulled. The length of the plastic tabs also plays a role in how the cover attach and come off. L1 and L2 need to be related. Because the cover is gone, the only way forward is to try out these dimensions and adjust them through a couple of printouts until the fit feels right. I also noticed the scan data from the viewer has a rough surface and quite a bit of noise. It looks like it might have come from a NIR scanner rather than a Resin one. For intricate parts like this, I would suggest using a laser scanner. It's faster and makes reverse engineering easier. Alright, let me show you how to make a clean 3D scan of a remote control's battery compartment. When you place it on the turntable and it wiggles like this, you need to steady it with some clay. The support clay shouldn't be too tall. Keeping it under 15 mm is ideal. Place the object firmly into the clay and make sure it doesn't move. For this demo, I will be scanning with a laser scanner, the Creality Sermoon P1. I'm scanning in 7-line mode for the finest detail, using a 0.15 mm resolution. In some battery compartments, you might even need 0.1 mm for the better result. During the scan, make sure to focus on the contact face where the cover sits. The scan needs to be captured completely. In certain areas, I switch to single line scanning to eliminate blind spots. It's also a good idea to remove the battery before scanning the compartment. Here's the scan result from the P1. It's noticeably sharper, smoother, and has much less noise. Let's compare this with the scan from the viewer. Clearly, the laser scanner delivers higher precision. There are no wavy lines along the edges or corners. This is a crucial quality in a 3D scan for reverse engineering because you will need to trace sketches along those edges. I also made a scan using the more expensive Creality Sermoon X1, and the results are even sharper with less noise than the P1. You can see this cutout area has a lot of noise in the P1 scan, but in the X1 scan there is no noise at all. Since this battery cover doesn't have a complex shape, I will use solid modeling and rely mainly on the extrude command. As I mentioned in my previous video, CAD models are built from sketches, either 2D or 3D. Most professional CAD software provides the same sketch tool, letting you draw lines, polylines, arcs, splines, and basic shapes like rectangles, circles, and ellipses. To create a sketch in CAD, you need a foundation, and the foundation is the plane. Different CAD plans vary in how they handle plane creation. Planes in CAD can be created in different ways by offsetting from the origin, defining them through points or axes, or referencing planes from an existing model. Sketch foundations and functions vary across CAD plans. Unlike the create command, some are faster and feature-rich, while the others are noticeably slower. For example, FreeCAD is quite slow and buggy when creating planes and sketches. So in this demonstration, I will use AutoDesk Inventor instead, since I don't have much time this week. In AutoDesk Inventor, I have already aligned the flat plane of the point cloud to the XY plane using Cloud Compare and adjusting in both vertical and horizontally. Next, I crop out the lower portion of the compartment to create a sketch profile. You can see that some of the point cloud walls aren't perfectly straight. This is an error caused by scan precision. I have left a gap of about 0.15 mm between the contact faces. Next, I extrude the sketch and pull it upward with the arrow until it touches the upper portion of the point cloud. I create a plane on this face and sketch a rectangle to cut out a shallow pocket. Right now, the cover shell is extremely thin, less than a millimeter, so I think I should add more thickness. Next, I fillet two of the corners using the point cloud as a reference. Next, I will create two tabs at the bottom. Since the scan data isn't really clear, I will have to estimate that size. For the thickness, I can't exceed 0.5 mm as seen in the point cloud cross-section. Next, I fillet around the base of the tabs to increase their strength. There is a cosmetic profile cut at this location, made with a simple sketch and extrusion. Next, I create a sketch for the push-in lock. Since the dimensions are only estimated, it might end up too long or too short, so you will need to experiment with the trial and error. The push lock tab is only 0.8 mm thick. I need to add a profile to lock the tab. Normally, the internal wall of the compartment would have a notch for the profiles to engage, but that detail can't be scanned, so the height of the profile has to be estimated. Next, I add two chamfers here. Then I make the final extrude cut to create the resting area for the cover. Okay, the modeling is complete. The cover may not fit the compartment perfectly, which I can tell from the scan precision during sketch tracing. Battery cover assemblies usually require very tight tolerances and minimum gaps between contact faces. There is no way to successfully print this battery cover with an FDM printer. It has to be done with a Resin printer. I'm going to print this using a Phrozen Sonic 16K with hyperfine resin. The print took about 3.5 hours to complete. In this video, I decided to show you the workflow for cleaning the Resin printer after use. First, tap the print off the build plate. I will use this console cleaner to remove the resin. It contains a silicone emulsion which dissolves resin effectively. One pack costs less than $1 for 40 wipes. It contains no solvent, just water and silicone emulsion. The resin comes right off easily. Cleaning the build plate is much less hassle with these silicone wipes. I have to admit, cleaning a Resin printer after use is hard work. The larger the printer, the more effort it takes to clean. Now the build plate is ready to be placed back into the printer. Next, I clean the tray so the resin vat can be placed on top. Then I slowly pour the resin back into the container. The larger the vat, the more strain it puts on your shoulders. Finally, I use silicone wipes to clean the FEP film. Avoid alcohol IPA as they shorten the film's lifespan. Washing takes 5 minutes and curing takes another 5 minutes. Support removal has never been a problem for me. You should remove the supports before UV curing, and with this print it barely left any marks. Here's the printing result. Notice the push lock tab, it's only 0.7mm thick, and the bottom one is just 0.5mm. You never achieve this with an FDM printer. The recessed edge is sharp and it's only 0.5mm height. A tiny bubble caused a minor defect, yet I have never had a failed print with this machine. Even with the standard resin, I think the tabs seem to hold up well. Okay, thanks you guys for watching. I'll see you in the next video.